This video discusses the average value of a function over a closed interval from a to b. This is the second video over section 5.2, the definite integral, for the OpenStax Calculus book, volume 1. Let's talk about what the average value of a function would represent. Let's suppose that you want to compute your average speed over a long car trip. Supposing that you start and stop more than once, you pass cars, you get slowed down, your speed is not constant. How then are you going to find the average velocity? In order to do this, in calculus, we take the trip and divide it into very, very small increments of time. Suppose we use n different increments of time. Then we can take the total time that we're driving and divide by n. That will give us a length of time corresponding to the length of each small increment of time, which we'll call delta t. We can take this formula then, and we can solve for the number of small increments of time called partitions, and that will give us the length of the time that we're traveling divided by the length of each tiny integral. That gives us the total number of time increments we're using. Then we're going to take each time interval and we're going to just pick a time in that small interval of time, and we're going to compute or sample the speed in that small interval of time with whatever it is at that particular value, say t sub I star. Then we can find an approximation for the average speed by doing the following. We can take each of these average speeds over each of the tiny little intervals for all of the n different intervals. Once we're done with that, we'll add them all together. When we're done, we divide by the number of integrals that we have. Now that we're done and we're down to this part, this means that we have the following. If we take each of those small intervals of time and we compute the velocity at that time, or the speed at that time, and divide by the total number of samples we took, that should give us a representation for the average speed over our trip. However, we can use the formula we developed up here to replace n. Replacing n would give us the sum of all of our sampled speeds divided by the quantity b minus a divided by delta t. However, when you have a complex fraction, remember you can solve this by, instead of dividing by the fraction, multiplying by the reciprocal. You'll notice that I've split the fraction into two pieces, the 1 over b minus a and the delta t here at the back. The next step we want to do, of course, is to figure out what this means in terms of the average speed. By taking the limit as the length of each time interval goes to 0, delta t going to 0, then we can get the limit of a Riemann sum. The Riemann sum's limit is the definite integral from a to b. Our average value we approximated with 1 over b minus a here times all of our sampled speeds, which is the sum from I equal 1 to n of our sampled speeds, times delta t at the end. By taking a limit of the Riemann sum, we can get not an approximation for the average value, but the true average value. This leads, of course, to the definite integral being equal to 1 over the quantity b minus a times the definite integral from a to b of f of t dt. In the textbook, they write the formula in terms of the variable x instead of t. Provided your function is continuous over the interval from a to b, which guarantees that you do have a definite integral, then the average value of that function over that interval is 1 over b minus a times this definite integral. You can also think of this in a different way. Remember that the definite integral actually represents the area under the curve between it and the x-axis. b minus a, on the other hand, is the length of the integral. So what you really have is that 1 over the length of the interval times the area should give you the average height of that function. And that's exactly what we mean. Since we're taking the area and dividing by the length, this should give us the height, or the average height, of the function. And that's what we're ending up with. If we let f bar, with a bar above the f, represent the average value of that function over the interval from a to b, then we can write the formula that the average value, which is equal to 1 over b minus a times the definite integral, implies that the width or length of that interval times the average height should give us the same area. In other words, length times height equals area. Let's move on to the next piece. In example 9, we want to find the average value f bar over the closed interval from a to b, then find some point c in that interval where f of c is equal to that average value. In other words, if my function is the square root of 4 minus x squared and my closed interval is from 0 to 2, what is the average height over that interval? And where is the value between 0 and 2 that has that average height? First, let's go to Desmos and graph the function over the closed interval from 0 to 2. You'll see here in the picture on the right that the square root of 4 minus x squared is the upper semicircle for the circle centered at the origin with radius 2. I've shaded in only the part from 0 to 2. I want to find the average value over that interval. Let's remember what the formula is. The formula for average value is given here. Let's take that formula and paste it down below. You'll notice here that I've rewritten the formula in terms of x since my function depends on x. Recall that in a definite integral, which has limits of integration, the variable you use for the differential does not matter because the variable disappears. A definite integral is a finite real number whenever that limit exists. That means there's no variable in the answer, so the variable you use is considered a dummy variable. However, to make it make more sense, I went ahead and used the same variable that the function is given with respect to. To compute this now, I need to find 1 over b minus a times the area between the function and the x-axis from a to b. Our a is 0 and our b is 2. In other words, I need to find the area of this 1/4 of a circle. Since the area of a circle is pi r squared, then the area of 1/4 of a circle must be the following. Area of a 1/4 circle has to be 1/4 of pi r squared. Since I can tell from the picture and also from the formula that the radius of this circle is 2, I can plug that into this formula to find the area of that 1/4 circle. 2 squared is 4, divided by 4 will give me 1, so that area is in fact pi. Now I need to take that value, which represents the definite integral part of the formula, and multiply by 1 over the width of that interval. My interval is from 0 to 2, so it is 2 wide. This means that when I'm looking for f bar, the average height, that I get 1 over 2 minus 0 times pi, which is the area, and this would give me pi divided by 2. That means that my average height here should be pi divided by 2. Now, if you take a calculator, you can compute that pi divided by 2 is about 1.57. Come to the y-axis and locate 1.5, which would be halfway in between these values. Just above that, we'll find the value of pi over 2. What does this mean then? This means that if I were to find the rectangle that extends between x equals 0 and x equals 2 and has height pi over 2, that the area under that curve must be exactly the same as the area under the quarter circle. If I were to color this in, I would find that the area in only blue and the area in only lime green are exactly the same. That is how you can find the average value of a function over a closed interval. This is a fairly simple idea, but it is incredibly powerful and gets used a lot in the real world. This is the end of the video and the last video over section 5.2, the definite integral. Now that we've found the average value over that interval, we would like to locate some point x equal to c in the closed interval between 0 and 2 such that the y value there is pi over 2. In other words, when we're looking at this picture, there must be some point on here that has that value. Let's see if we can find it. From the picture, it is clear that that point must be right here where the purple ball now appears on your screen. Right here is on the semicircle, and it also has height pi over 2. Let's see if we can find the c value by plugging it into our function. In order to do that, we need to write the equation and let it be equal to f of c. That means that f of c, which has got to be equal to the average value of pi over 2, has to also be equal to the square root of 4 minus c squared. Since that's equal to pi over 2, in our next step, what we should do is square both sides in order to get rid of the radical. By squaring both sides, I can eliminate the radical. This will give me pi over 2, the quantity squared, equal to the square root squared, which just lifts off the square root. This will give me the 4 minus c squared underneath the radical, and will result in pi squared over 4 on the left. Now, in order to solve for c, I need to move things around. C squared then must be equal to 4 minus pi squared divided by 4. In order to find c squared, I could take a common denominator, which would be 4, giving me 16 minus pi squared divided by 4. Since c must be between the closed interval endpoints of 0 and 2, I know the value of c must be strictly positive. When I solve for c then, I only need the positive square root. This will give me the positive square root of 16 minus pi squared divided by 4. I can split the radical, which will give me division by 2, but I cannot split the radical in the numerator since those are separated by subtraction and not multiplication or division. In order to know what that value is, you'll have to use your calculator and approximate. On the calculator, I get approximately 1.23798 with more decimal places. This is roughly 1.24. This would be at about 5/4. Let's look at our picture and see if we agree. If that is the case, then over here somewhere at about 1.5/4, I should have the y value of pi over 2. It looks like it could be relatively close. In fact, I could be just a hair off on my ball, but it looks like it's somewhere in that region. Thus, I feel pretty confident that that must be the value of c. In the next video covering section 5.3, we will be talking about the fundamental theorem of calculus.